All right, we're stepping up to lathe here. I just want to show you a couple things on speeds and feeds and depth of cut. So the biggest piece of making sure you can do everything, to its full potential of the machine is making sure everything is set up rigid. So when you're holding your material, if you can keep it stubbed up here inside the chuck as close as possible to the chuck face, your material is going to be better supported. If this was sticking out another, 3, 4, 5 inches, I can't do as much with the machine as I would like to. When it gets so long, what you actually have to do is put a hole in the end of it with a center drill and use the live center to support it so you can actually keep the part rigid. So right now, I'm stubbed up pretty nicely here. Make sure this is good and tight on the 3-jaw, happy with that. And now I'm gonna put my tool in. I'm just gonna use a right-hand tool here. Again, I'm gonna make sure that I'm not sticking too much of that tool out, so I'm gonna stub this up pretty decent, just so it's nice and solid. And lock down pretty effectively here. Looks good. Then, another thing you can do here, if you're worried about rigidity, is your compound. If you have that sticking out too far, it's losing support underneath of it. So what you can do if you want to be very, very solid on your machine is back that off a little bit and then bring your tool up in that direction. Now you can see it's supported well underneath of there. It's going to make a lot more solid. And I'm just going to turn this forward just a smidge. All right, so the material I have here right now is 12L14. 12L14 falls in the family of a low carbon steel or a mild steel. Those are the same family. I'm going to measure my diameter. And I can see that I'm at inch, yeah, it's just under 1.25 inches, so it's 1 inch 250 thousandths. So I know nothing about my speeds or anything right now. I need to calculate that all out. I'm going to set all my power feeds and everything as well. So get your trusty calculator. The formula again for low carbon steel or mild steel is going to be a range of 70 to 100. Well, today we're just going to go, normally I say start in the low end. 12L14 is the friendliest of all low carbon steel, so I'm going to go even a little higher. I'm going to say 85 surface footage. So I'm going to go 4, which is my constant. I'm going to use that every time I do my formula. 4 times the surface footage, so I said 85. And then I'm going to divide that by the diameter of my stock. And the stock measured 1 inch 250 thousandths. All right, so it says I should go 272 RPM. Well, I have an option of 179, 256, or 351, so we're going to go 256. So I'm going to go into silver there and silver here, and my RPM is set based on my surface footage running at 85. I am going to choose 256 RPM there. Then I'm going to my gearbox and I just set the power feed. Remember, the feed is in thousandths per revolution. So what's interesting about the lathe is if the revolutions increase, the feed will increase physically. You'll see it change because the feed rate's always based on the carriage to the spindle, and it feeds in inches per revolution. So with that being said, we're going to set this, and we're going to be doing roughing cuts right now. So I'm going to set this for 10 thousandths. And again, you could set this for 8 thousandths. You could set this for 12. The more horsepower and the larger your machine is, I've seen some people be able to rough up to a feed rate of 20 thousandths per revolution. That takes a lot more horsepower than what this machine has. So 10 works pretty legit here, and 10 works pretty much across the board. Even in the big CNCs, I don't go much bigger than 10. Maybe I go 12 on a good day, but that's kind of a good roughing feed. So we go down to our gearbox here, and we can see 10 thousandths is right there. So that's the third column over. So we're going to flip the pin here, set it to that one. We're going to set it in A, which is over here, and then we need to make sure that we're in F. So everything lines up basically A, F, and then column 3 here, and we're in F right there, so that's good. Our RPMs are set. All right, we're ready to turn this on. So there's our spindle RPM. So for starters here, we're just going to come up and make sure my tool is solid. I also should just verify before I get started here that our steel rule is roughly on center. It might be just a little bit high. Drop that down just a smidge. That'll work. Okay, so now we're gonna go and just do some rough cuts on here. So, come up, make contact, and I'm just gonna zero this out so I know where 0 is at. So right here, set that at 0. And our first cut here, we're gonna take, we'll take 100 thousandths. This is 100 thousandths off the diameter. So it's 50 thousandths on this side of it, but it's also gonna take 50 thousandths on the opposing side of it. And as I'm doing this, I definitely want some coolant. And we're feeding it again at 10 thousandths per revolution. So, come into our cut. If everything is solid, you can see the chips break up nicely, and we get a pretty decent cut there. And I'm just doing some practice cuts here so you can kind of get an idea how this works. Just to help solidify what we've been talking about with material removal rate and all of that. And we can kind of see what that cut looks like. Seems to work pretty good. So I don't have a specific area I'm going to. I'm just turning for the fun of it. So I'm going to stop it, I don't know, about here. And back that off, come back. All right, so that was 100 thousandths, again, off the diameter. So I took 50 thousandths per side. So it's always weird. The orientation of here actually only moved in 50 thousandths on this side, but on here I had to move it 100 thousandths, and that's because this here dial on the cross slide deals with diameter. So it's physically only gonna move at 50 here, but at 50 here moved, and it also took 50 off the backside, so the diameter changed by 100. So that was a 50 thousandths depth of cut. So again, you know, depending on how your machine reacts, you can kind of play with your depth of cut, and it's the most minimal effect that's going to happen to your tool life. So if I were to take the RPM right now and double it, I mean, I can probably toast that tool very quickly. But by taking my depth of cut and doubling it, it's probably not going to do much to a tool life. So I'm going to turn this on again, and this time, in theory, if I really wanted to get fancy here, my diameter has changed now from 1 inch 250, and now it actually measures minus 100 thousandths, so it's 1 inch 150. So if I really wanted to, I can actually increase my RPM potentially. So watch this. If I go 85 surface footage, 4 is a constant times 85 divided by 1.150. All right, now I can go 295 RPM. Okay, I'm still not close enough to that 351. I'd feel comfortable moving up to that, so I'm gonna leave it. But if I did the math and it came closer to, you know, 340 or something, I probably could just up that RPM. So we're gonna leave that right now, but what we are gonna do is come back and just make touch contact again, and we're gonna zero this out, and this time we're gonna take a bigger depth of cut. So last time I took 50 thousandths per side, or 100 in the diameter. This time I'm gonna do double that, just to see how it reacts. So this is gonna be 200 thousandths off the diameter and 100 thousandths depth of cut. And again, you need to make sure, if you're gonna try this, that your machine is all set up correctly, everything is solid and rigid, and if something bad happens, you're ready to pull the trigger quick and kind of back it off. But I think we'll be okay here. You can see that depth of cut. You can see the chips are rolling off there nicely. I don't hear any barking or squeaking or groaning from the machine. It all seems to be cutting effectively. And